Hello everyone, thanks for coming. And today I would like to give a review of what we have learned in this week: discrete distributions in actuarial mathematics. So, where is discrete modeling, discrete distribution used in actuarial mathematics? For instance, when estimating the number of claims, we usually use discrete distributions. For severity of each claim, we use continuous distributions. For instance, to model money to be claimed. But for the number of cases, the number of claims, we are using discrete distributions. In actuarial mathematics, we are caring more about discrete distributions when the random variable can only take non-negative values like 0, 1, 2, because the number of claims is non-negative. So the important concept is the probability generating functions. The probability generating function is defined as P of z to be expectation of z to the power n, where n is a random variable. So it's a summation of pk times z to the power k. Pk is a probability that the random variable n takes the discrete number k. If we take the derivative with respect to z for the probability generating function and z equals to 1, then it's the expectation of the random variable. If we take higher order derivatives to the degree to the order n, then at z equals to 1, then it is the expectation of n times n minus 1 to n minus n plus 1. Also, the probability that the random variable n takes the value m is taking the derivative of the probability generating function p to the order m divided by m factorial at z equals to 0. So essentially, the probability generating function contains all the information we need for the discrete distribution when the random variable capital N can only take non-negative values. A special case, also an important case, is the Poisson distribution. We say that a random variable x obeys the Poisson distribution with a parameter lambda if pk is e to the power minus lambda times lambda to the power k divided by k factorial. Here, k can only take non-negative integer numbers like 0, 1, 2. The expectation of the random variable x is lambda and the variance is also lambda. Furthermore, the summation of several independent Poisson distributions is also a Poisson distribution. We prove this by using the probability generating function. Notice that here the condition is that the several distributions are independent of each other. Finally, we have the binomial distribution class. We have the binomial distribution. We say that the random variable x obeys the binomial distribution if it can take the integer value from 0 to n, and the probability that it equals to k is given as follows. The expectation is n times p and the variance is np times 1 minus p. So p is like the successful probability, and we are repeating an experiment n times. We also have the negative binomial distribution, and this is the probability that the random variable takes the value k. So here, R is like the number of failures before we stop, and beta is the relative rate of success. Beta over 1 plus beta is the true probability of success. So essentially, we stop after we reach R numbers, R or R values. So the expectation of the random variable x is R times beta. So on average, we will stop after we repeat R times beta times, and the variance of the random variable x is R beta times 1 plus beta. So the Poisson, the binomial, and the negative binomial, as well as many other discrete distributions belong to the AB0 class, which means that the probability that the random variable x takes the value k is A times B divided by k times the probability that the random variable takes the value k minus 1. Thanks for listening.